Hello and welcome back to another Pore Lab lecture series. Our today's speaker is Dr. Patel Ravi, a researcher at Institute of Building Material at Karlsruhe Institute of Technology in Germany. Dr. Ravi obtained his PhD in civil engineering from the University of Ghent. His PhD thesis was focused on modeling changes in microstructure due to degradation process in cementitious materials. During his PhD thesis, he developed a lattice-Boltzmann-based pore-scale reactive transport code called YANTRA, which is capable of simulating changes in pore structure under chemical reactions. His research areas span over a wide range of topics, such as development and application of different numerical methods, such as discrete element method, lattice-Boltzmann method, particle method, finite element method, and development of multi-scale and upscaling strategies for geomaterials. Today, he's going to talk about modeling complex degradation processes in concrete structures across material scales. Thank you, Dr. Ravi, for accepting our invitation.
Hi, Mohammed. Thank you for inviting me, and it's my pleasure to be there virtually at Pore Lab, talking about my research today. What I'll do now is I'll quickly share my screen. Yeah. Is it shared or not shared? No. Share one, share screen. Yeah, I think now my screen is shared with you.
Yes, it is.
And yeah, so like Mohammed mentioned, only recently, just this month, I moved to Germany from Switzerland. So I'm still in the transition move for the new job. What I will do in the next 30 to 40 minutes, just give you overview about my research activity, specifically focusing on degradation processes for concrete structures. And also I will tell more about myself, because maybe many of you are not familiar with me. So this is a good opportunity for me to introduce myself to you. So let's start up by a little bit information from my side. So I am Ravi Patel. I did my PhD in civil engineering from Ghent University. My PhD was funded by Villgen Nuclear Research Center, and there we were specifically looking for degradation of cementitious material over long-term in nuclear waste disposal system. This required us to then go towards lower scales and to see how actually the material evolved right from the pore level and how it impacts at the scale of a repository. As a part of this PhD, I developed, like Mohammed said, a new framework based on lattice-Boltzmann method to study such complex degradation processes, mainly focusing on physico-chemical processes. After that, I was working for 1 year, again with Villgen Nuclear Research Center to further do research on pore-scale modeling related to cementitious processes, but also then focusing towards clay minerals. Since 2017, I was in Scherrer Institute in Switzerland. In Switzerland, I was awarded Merit II Fund Fellowship, where we were looking into the combined effects of carbonation and leaching. So it's two opposing reaction. One is dissolution, one is precipitation, and how this affects the pore structure, and how to model this and how to upscale these processes. Last year, then I got a further extension to my contract at Scherrer Institute, where I was focusing on multi-phase flows. And from this month onwards, I am starting at Karlsruhe Institute of Technology in Institute for Building Materials and Material Testing Laboratory as a group leader, where we are developing a new group focusing on numerical modeling and digitization in civil engineering. So the scope of this group is a bit broad, and I will talk a bit more about the scope of the group. To summarize my research experience till now in porous media, or porous materials, which is the core idea of Pore Lab. So my research can be broadly divided into three parts. One is concrete structures, second is software development, and third is diversification, that is application of the developed tools to other fields than the field of my interest or focus. So as a part of software development, I focus on development of two particular softwares. One is Yantra Multiphysics, which stems from my PhD thesis, which is based on lattice-Boltzmann methods. And here we are focusing on pore-scale modeling. And what we are trying to do with this tool is we are trying to develop a tool which can do multi-physics processes, not just flow or transport, but you want to focus on combined flow, transport, thermal gradients, and material evolution due to dissolution, precipitation reactions. And the second set of software which I focus on development is PoroPhi, which is based on a finite volume code Phi, but focus more towards porous media modeling, which I use for continuum scale, which I will show you a bit more in detail. About these two tools. Then in terms of application of these tools, it goes towards concrete structures and other diversified fields. Till now, the key applications in the diversification zone I can list here. The recent one was thermohydraulic modeling for full boiling in nuclear reactors. Then I also had a collaboration as a framework of exchange PhD students from University of Oslo in Norway, where we were looking into dissolution precipitation for caprock integrity for CO2 sequestration applications. Also, I have a current collaboration in Germany where we focus on the effect or water transport properties due to the effect of mucilage, which is in the rhizosphere, how it affects the water transport, because this can lead to hydrophobicity or hydrophilicity near the particle surfaces. And this has a very interesting effects on how the transport processes or water transport evolves in such systems. Talking about concrete structures, till now I worked on the multiscale modeling of transport processes, and this I will talk about in a detail. Then I've been focusing on nuclear waste disposal system till now, where I'll be looking into transport in cement and clay systems, degradation processes such as leaching, combined carbonation and leaching sulphate attack, and imbibition and water transport in concrete. More recently, I'm also trying to develop tool sets or trying to develop models which can enable, which can enable in silico design of new materials. So this is the research in very nascent stage. So I will not talk about this, but I would mainly focus about these two topics in my presentation. So as I said, now I'm moving to a new job in Germany, where we are starting a new group, which is focusing on numerical modeling and digitization. And in this group, we focus on three key challenges which are currently faced by construction industry, mainly to move towards sustainable materials and material recycling, to deal with the aging infrastructure, when to repair, how to repair, and to move towards digitization of construction industry, and that is Industry 4.0, where the machines and components are connected, and how this can be linked in a construction sector. This research or these challenges are being addressed by combined skills which I have gained over the course of last 10 years during my PhD and postdoc experience. That is, by training, I'm a civil engineer who focuses on material science, and who has learned the skill of scientific computing through my postdoc and PhD experience. What allows with these skills, it allows me to focus on different areas which can provide answers to such grand challenges, such as multiscale modeling, which is the topic of today's presentation. Then material informatics, that how we can use data to link, the thermodynamics of chemistry and properties of cementitious material. Also, topics such as machine vision, which can be used to characterize damage in concrete structure, material optimization, and Internet of Things. So these are the topics which are currently still under development with the framework of the new research group. So maybe this is something which I can talk about in coming years. And today I focus on multiscale modeling. So to begin with today's topic, let me start with the motivation. What drive my research in the last 10 years to go towards multiscale modeling of concrete structure? The main motivation, as I mentioned, was nuclear waste disposal system. These are very complex structures where long-term durability, we are talking about 10,000 years, 1 million years, is of great concern. And how this system evolves, this requires a thorough understanding of how materials behave in the system. So, under such system, the structure of material undergoes through a complex external gradient, that is temperature gradient, mechanical gradient, chemical and physical gradient, which leads to wide range of deterioration processes. And therefore, the fundamental modeling becomes rather the only tool to deal with such problems. And that's what was funding my research till now. What I can see also as an extension of my research is that currently in civil engineering, particularly concrete science, we are focusing on new innovative materials, which have not been applied for a long time in the field, and how to extrapolate their applications to the field conditions, and how to know how this material will behave over long term. For this kind of questions also, multiscale modeling and fundamental modeling becomes very important. So to begin with multiscale modeling, we first need to know the scale which we are dealing with, right? For concrete structures, the scales, it's a very hierarchical material, starting from the nano level to the macro level. So the scales there are several intermediate scales. One can start right from the fundamental building blocks of cementitious material, which we call as CSH, which is nothing but amorphous phase consisting of calcium silicate hydrate. From there, one can go towards a little bit higher view, which is at the micro scale, which deals with the cement paste itself. So cement paste itself consists of varieties of mineral constituents and a porous matrix. And when we are talking about concrete structure, it's not the cement paste which is of interest, but concrete itself, which is of interest. And at the scale of concrete, we have aggregates, which are basically forming 50 to 60% of concrete matrix, and then cement paste. And the interface between aggregate and cement paste, which has different properties from the bulk cement paste itself. And so if one needs to address multiscale modeling, one has to cover all of these scales, right to the scale of the reinforced concrete structures. And this makes it very challenging and at the same time very exciting. What we need to do for such kind of multiscale modeling is we need to first represent our material. So this leads to a challenge to number one, which is microstructure representation. Once we have microstructure representation, this is just the starting of the story. Then we would like to know how the material evolves over time. And this requires a set of models and tools which can allow us to develop, which can allow us to simulate the evolution of material over different time scales and accounting for different physics. After we have these two categories sorted, then it comes to what we are producing from the models. That is validation of models, parameterization of models. And a final challenge which remains is how to link such a hierarchical structure in a one modeling framework, that is to bridge different scales. So these are the topics which I have tried to address in my research. And this is what I will give you a little bit overview about. If we talk about models which are used in civil engineering, we can divide models into two types. Like one would be the models which engineers use for design. These are basically very simple and crude abstraction of actual physics. If we are interested in physics, for instance, material design, or if we are interested in knowing what is the long-term evolution of the material where we don't have any experimental basis, then we need to go towards a more focused modeling, that is a bottom-up approach. And these are the models for knowledge or fundamental material models. So these are the categories of models, and these are the challenges when we deal with fundamental material models. So let me now start with addressing each of these challenges the way I address it, and to give you some example results on this topic. So the structural representation of concrete at different scale has been of interest since more than 20 years. People have developed models at each scale of concrete to how to represent the material. And what I do is I basically take this knowledge and combine it. So at the scale of CSH or at the nanoscale, we have different models, the models which we can use. For example, analytical homogenization, and models which basically give the representation of 3D structures. At the scale of cement paste, there are different types of model again, but we can classify them probably into two categories of models, which are basically shown here. One is basically shrinking core models, which basically shrinks the dissolving phase, and the sphere expands for the precipitating phase. And another one is like a random automation-based models. Both these models are very interesting because what these two models do is they give you same evolution or same, let's say, phase constituent. So if you make a volume fraction of different phases, they are same at a given time or at a given degree of iteration. However, they are completely different in terms of representation of pore structure. For instance, in one model, you can have complete depercolation of large pores. And in other models, you can always have large pores connected. So you have pores ranging from few hundred nanometers always connected, whereas in one case, it gets disconnected completely. And this can lead to different properties and behavior. So it's very interesting to test both these models. And this is what I normally do for my research. At the mortar or concrete scales, the representation of aggregate as spheres is more or less considered as a suitable representation. And this has been demonstrated by different researchers doing studies on different shapes of aggregates. So this is a representation normally I stick with as a spherical distribution in a 3D space. And then one has to represent the interface between the aggregates and cement particles. For this, I use so-called ribbon model, which basically provides me a gradient of water cement ratios between the aggregate surface and the bulk cement phase. With this, I can calculate what are the phase constituents in this interface zone and what is the phase constituent in the bulk cement phase. So that's how I represent materials at different scales. Talking about numerical, second challenge, that is simulation of physico-chemical processes. For this, I developed different tools at pore scale, so at micro scale, and at the mesoscale of material scales. I use a Lattice-Boltzmann method-based framework, which is both multiphysics and multiscale. Multiscale in the sense we can account for voxels which has unresolved porosity, and I will show you examples of that, and resolved porosity at the same time. So this numerical tool at the moment can simulate fluid flow, mass, and heat transport. We also simulate reactive transport. For reactive transport, we have coupling with the thermodynamic solver Frixie, if you are aware of that. What Frixie does is it calculates geochemical equilibrium and kinetic reactions, and from these reactions we can apply sourcing terms and evolution of geometry. Then we have algorithm for multi-phase flows based on lattice Boltzmann method, and more recently particulate reactive flow, where basically you have moving particles, you have reactions on the surface of particles, and you have fluid flow. So this tool was released as open source during my PhD, and I continue to maintain it since then. Coming next year, there will be a major upgradation and also a transfer of repository to GitHub. And then all of this physics would be accessible for open source for the entire scientific community to download it and use it. So that is something which is currently I'm working on to make it more accessible and open source. For next set of tools in the current open source version, what you can do is fluid flow, mass transport, and reactive transport. These are the only facilities available online right now. To go from mesoscale, so that is the scale of concrete explicit representation, to concrete structures, I developed then another set of tools, because at this scale now it becomes very interesting to use unstructured mesh rather than structured mesh. And so what I do is I rely on the set of numerical tools and I bring them together to make one holistic framework which can deal with thermo-hydromechanical processes. Here is an example of such a simulation where we have combined chemical evolution with mechanics. So this is a chemomechanical simulation for sulphate ingress, where you can see the ingress of sulfates and you can see the cracks and damage developing. For this, what we do is we combine a GUI or preprocessor, which is Salome platform. It allows us to create the mesh and the structure. Then for solving physics, we use finite volume methods, which is implemented in PHI, and finite element method for mechanics. And these both tools are combined together. And then for chemistry, we use geochemical solvers such as Frixie and GEMS. So having given you an overview of microstructure or structural representation and numerical tools which one can use to simulate physico-chemical processes, now I would like to bring your attention towards some applications which I have done on this area, starting first with the multiscale modeling of ion transport in cementitious materials. There are two key papers on this topic which I have published and which I will talk about now. This paper, first paper, deals with understanding the role of different porosities in cement material. That is the nanoscale porosity and the porosity at the microscale, where the nanoscale effects become redundant, how they interplay. And the second paper deals with charged ion transport processes. So when you have like a charged surface at the nanoscale, how this impacts ion transport at the cement paste level. This is the focus topic for the second application. So for the first paper, to understand, we want to understand nanoporosity and microporosity and what is the interplay between these porosities. Like here you can see in cement, we have porosity ranging from 1 nanometer right up to a few tons, up to a few microns. So for this, we take a look at the concept of percolation. The concept of percolation is very simple. You have two phases. One is the phase which is nanoscale dominant. One is the phase which is where microporosity is dominant. If the nanoscale porosity is completely percolated, the transport pathways follow nanoscale porosity. If they're not percolated, then it follows microscale porosity. So how do we understand whether this is really important to distinguish? What we can do is numerical simulation to understand whether this distinction makes sense or not. So what I did during my PhD is we used two different simulation models, like I mentioned initially, and that these two models, they give same porosity, but they give completely different pore structure. In one case, you can get completely depercolated large pores, and then the nanoscale porosity becomes dominant. In other simulation case, the big the pores at 100 nanometer and larger are always percolated. If we just take the microstructure from these two models and then we do run simulations, we can clearly see the effect of depercolation. So for instance, if I compare here with the model simulations and experiments with the model one, which is represented in blue over here, which does not depercolate large pores, you always get a higher values of diffusion coefficient. And the model two, which basically leads to depercolation at around 20% of capillary porosity, which is porosity above 100 nanometers, you can see a sharp drop of diffusivity. Which so if you want to really reproduce experimental results, we need to account for this depercolation, and this was one of the important findings which was established through these simulations. What we did then is to further extend this work to account for surface effects at nanoscale. What we observe experimentally, as for instance, is anions or negatively charged ions. Basically, they diffuse faster in cement pore space compared to the positive ions. And H2O more or less, or water more or less, has a similar diffusivity as tracer has similar diffusivity as positive ions. So the fundamental reason for this discrepancy can be thought of as a surface effects which are happening at the nanopore level in cementitious material, where you have calcium silicate hydrous phase, which is negatively charged, and therefore it attaches calcium ions, so which is the first adsorbed layer. And basically at the end, at the zeta potential of this surface is positive, which can then increase the ion transport near the surface. So to simulate this process and to understand this more fundamentally, we developed a multiscale model starting from the description at a nanoscale. So we took a nanoscale model, and from nanoscale model, we try to simulate process at the level of 1 to 2 nanometer pore size, and from there to up to 100 nanometer pore size to 1 to 10 micron pore size. For this, we start with a model which is based on molecular dynamics, which basically gives me the distribution of ions near the surface based on the surface charge. And this distribution does not follow the classical Poisson-Boltzmann relationship of Nernst-Planck equation. So what we have to do is we have to modify the Nernst-Planck equation to account for the hard sphere context near the surface. With this modified Nernst-Planck equation, we can compute the diffusion coefficient at the scale of 25 nanometer REP. And from there onwards, the nanoscale or surface charge effect becomes less dominant, and we can apply Fick's law to the higher scales based on this diffusivity which we computed. So this is the kind of higher scale upscaling scheme which we follow to predict ion transport from the fundamental level, right from the surface effects to the cement paste level. What we were able to do through this numerical simulation, we were able to clearly distinguish the effect of a negative ion transport versus positive ion transport in our model. However, what we were not able to do was we were not able to correctly capture the magnitudes of our values. And the reason for this lies in our poor representation of the structure. So this representation of hierarchical representation of microstructure is rather rudimentary. And now through the CT scans and through synchrotron tomography, we are knowing more and more about the structure of cement paste and it is becoming more and more clear that there is more to this story. And for this, therefore, we need a scaling factor to scale down our simulation to experimental values. So what we can do fundamentally is we can capture the basic qualitative trends correctly. And this is one of the important contributions of this work. From ion transport towards modeling more complex degradation processes, which involves material microstructure evolution. First set of studies I did was on calcium leaching. Calcium leaching basically refers to a process where you bring water in contact with cement paste. Cement has a pH of around 13.5, and when you bring a water which has a pH of around 7, the calciums which are there and other alkali ions which are present in cement solution, they start leaching out of the material, and this leads to dissolution of mineral phases in cement. Calcium, most of the minerals are calcium rich. This set of mineral forms around 60% of traditional OPC concrete. So that's why this process is often referred to as calcium leaching process. For calcium leaching, we did simulation at different scales, right from the micro scale towards the mesoscale, and we were addressing different set of problems over here. This set of simulations were to understand the leaching process itself and whether we can capture the microstructure evolution fundamentally, whereas this set of simulation were trying to address a question whether we need to study leaching kinetics at a mesoscale or at a mortar scale, or if I know the leaching kinetics at the cement paste scale, I can basically predict something at mortar scale without any complex upscaling. So this was the question we were trying to answer in this paper. So let me start with first microscale or cement paste scale. In cement paste scale, the simulation domain is shown here. And like I said, we just bring water in contact with one of the surface and we allow the system to evolve. And basically with time, you can see here this pink material, which is basically Portlander or calcium hydroxide. This would dissolve, and then this yellow material, which is basically CSH, which will decalcify. So you can see here we have two representations. One is the nanoporosity, which evolves like a continuum scale simulation, but that is basically you need a relationship between porosity and diffusivity, and then a pore-scale simulation, which explicitly represents a pore structure. So from this simulation, I can know how the nanoporosity is evolving and how the microporosity is also evolving because of the dissolution of these bulk phases like Portlandite. So these are like example set of simulations. You can see here in this paper, we have used both microstructure representations, and they give very interesting results. Basically, because in one case, porosity can be depercolated, the large porosity can be depercolated, in other case not. And here you can see example pictures where you can see the calcium ion profiles, you can see the Portlandite profile here, and then the CSH calcium profile over here, for instance. The kind of information we get from the simulation is shown here. We can get, for instance, pore space evolution, like how the capillary pores evolve with time. The connectivity of pore spaces, and this is very interesting when you compare different models, that you can have at some point certainly all the pores percolated, and then your mass transport increases quickly. Time evolution of the calcium in the solid phases, and basically the profiles of the quantities like the calcium porosity and things like that. From these simulations, what we were able to do was we were able to quantify, and we were able to show that from microscale models, we can basically predict quite reasonably the leaching fronts. And this was a very important contribution from this publication. What we did then is we applied the same model at the mortar scale. what I mentioned, what I forgot to mention in previous slide is that we also did certain certain numerical treatments to make our simulation faster. This involved creating lookup tables instead of using full geochemistry. If you are more interested in how the whole model is implemented, I would suggest to take a look into the paper. At the mortar scale, we were interested in looking into the effect of this interface transition zone, which is more porous, and how the percolation of this interfacial transition zone affects the leaching kinetics, or whether it has an effect or no effect at all. Here are the simulation snapshots. You can see we can capture calcium concentrations, Portlandite evolution, CSH evolution, total porosity evolution. What was interesting in the simulation was we were able to establish that at the mortar scale, the leaching fronts progresses at the same rate as cement paste scale. This was something which previous researchers have speculated from experiments, but it was never proven fundamentally. And the reason for this was something which we were able to establish from our simulation, that in case of mortar, you have two phases. One is basically the aggregates, which is increasing the tortuosity. And the other phase is this interface transition zone, which is increasing the diffusivity. When these two interplay, they cancel the effect, and the net effect is we have a front which is same as that of cement paste. And we can apply a simple scaling to basically understand the, we can apply a simple scaling based on aggregate fraction to calculate the leaching kinetics right from the cement paste level to the mortar level. So what it means is that we don't need to do any upscaling. If I know something at cement paste scale, I can basically predict the evolution of material at the concrete scale. So this was the these were the topics which basically deal with dissolution. Now, more recently, we extended our applications to processes which are which have a kind of a competition between dissolution and precipitation. For this publication, what we did was we were interested in simulating how the cement microstructure evolves with time when it is in contact with carbon-rich water. So when you have a carbonated or carbon-rich water, what happens is basically you have calcium in the cement pore water, which reacts with carbon to precipitate calcite. At the same time, the pH of the ingredient solution is lower than the pH of the cement pore water, and this leads to the leaching of calcium ions. So there is a two competing effect, and how this interplays. So for this, we develop a simulation at the microstructural level of cement paste, where we represent capillary pores, the large pores, the nanoscale porosity, and basically the different mineral constituents at the micro level. The novel thing in this model was we were accounting for subvoxel or nanoscale porosity evolution, both due to dissolution and precipitation, and also we account for this nanoscale porosity while representing the precipitation of calcite phases, because it's been shown experimentally that the calcite precipitating on the surface of cement minerals is not completely blocking the transport pathway. So we have like a multi-level or two-scale representation of process. So here is the boundary condition for simulation, which is basically carbon ion in the boundary solution, which leads to carbonation. This setup was very close to the experimental simulation by Jukic and Scherrer, which were focusing on evolution of cementitious material in well bore for CO2 sequestration. So here is an example output from our simulation. This was the simulation where we did full geochemical coupling. with the transport model. So you can get information on different ions. You can get information on pH, and you can also get the evolution of microstructure like precipitation zone, which is developing, and dissolution zone, which is developing. So here is first set of output from the simulation. What we can distinguish clearly is from where the calcium is leaching, which phase is the more dominant phase when it comes to the leaching of calcium. And it was found that the calcium hydroxide, which is calcium much faster than calcium silicate hydrate. What was also interesting was we were able to capture which porosity evolves quicker. So it was shown here that the capillary porosity changes much quickly compared to, and the calcite gets much quickly precipitated in this capillary porosity because the transport process is much faster in this porosity compared to the nanoscale porosity, where after some point the precipitation of calcite is almost stagnant. And what is interesting to note is that the porosity does not need to completely clog to retard the calcium leaching. So even a small changes in porosity can have a significant impact on the way the kinetics of the system is evolving. What we were able to also qualitatively capture was different layers which were observed in experiments. Like in experiments, we observed that you have a zone where the portlandite is completely depleted, and you have a calcite precipitation zone, and you have a zone where there is a extensive degradation, that is the leaching from both portlandite and calcium silicate hydrate is seen. And here you can see the phase diagram for given time, and we can clearly distinguish different zones. You can see here is the zone where the portlandite is basically dissolved completely, and the calcite is precipitated, and then the CSH is dissolving, which is highly degradation zone. Also, what you can see here is we can basically distinguish between the calcite precipitated in subvoxel pores versus calcite precipitated in the bulk phase or CSH phase. So to summarize my presentation, I try to give an overview rather than giving a more detailed view on one specific topic on my research. Basically, I demonstrated that there are material models which allow us to do multiscale simulations. However, this should be taken with caution because these models may not be representative, and this is still a very active area of research on how to represent material microstructure. Secondly, when we talk about the new or no cementitious materials, at present there are no comprehensive models to present this kind of pore structures. What I also demonstrated is with the tools which we have now at our disposal, we can simulate complex physico-chemical degradation processes with unprecedented details. So we have like a vision to see how material is behaving at different scales. Of course, one can basically start improving algorithms, make this model more parallel to do more larger simulations and couple more physics, but the fundamental toolbox is available now. What is important to do in the future research would be to create a new set of experiment, and this is where I always struggle to get a nice experimental data to validate the models. So we need to create a new experimental database which can help to model, which can help us to validate models at such a detailed scale. At the same time, help us to derive different parameters which are needed as model input. So these are something which I always see as an active area of research for the coming future. Finally, talking about multiscaling or scale switching, what I've demonstrated in today's presentation is that we can basically reach scales for transport processes. We can also demonstrate it for some kind of applications. You don't need to actually do upscaling. You can basically establish that simple scaling laws can work. However, when it comes to a complex processes where you have combined dissolution and precipitation, you will need a more comprehensive approaches for upscaling and scale preaching, and this is something which is an area which I would like to actually work on in future. To conclude and to give a food for thought, what is the importance of multiscale modeling when we're talking about concrete structure as a civil engineer, right? So thinking beyond multiscale modeling, one can think of the modern computational tools and structures. They can be linked fundamentally. For instance, we can link data science, multiscale modeling, and structural engineering. And there already exist certain links between this domain. For instance, structural engineering with data science, we can talk about structural health monitoring. For example, if you want to talk about multiscale modeling and data science, then we can use machine learning to create reduced order models or surrogate models. Or we talk about structural engineering and multiscale modeling, then it's basically classical structural design. What is the challenge for the coming future is to develop integrated solutions which lies in the interface of these three topics. And this is something which we will focus on in KIT in coming years. With this, I would like to conclude my presentation, and I would like to thank you for your attention.
Thank you so much, Dr. Ravi, for the nice presentation. Is there any question? And is there any question from the Zoom participants? You can just unmute yourself and then ask the question. Okay, thank you so much. And yes, and have a nice day.
Thank you.
Thank you.
Bye.
Bye.